So as I promised, this is regression, right? We're just guessing the value of a function using data. The question is, how do we do that? How do we use data to guess what that conditional mean function actually is? And this is a general recipe for regression, not just linear regression, regression writ large. It's always these three steps. Step 1, pick a set of candidate functions. Step 2, pick a way to grade how well a candidate function fits the data that we have. And then step 3, we develop an algorithm that searches our set of candidates for the one that fits the best. So let's dig into this. And first, let's talk about what do we mean by a set of candidate functions. So here, let's say we have these data, our pink data points here, and they represent the relationship between y and x, y being some outcome and x being some predictor of that outcome. So maybe y is how long people live after being diagnosed with a particular disease, and x is some measure of their health at the time that they were diagnosed, or like the stage of the disease or something like that. And we just want to figure out exactly what that relationship is. So here what I'm showing is f1, f2, and f3 are candidate functions. So these are three different functions that are just totally made up that I'm saying these could be the conditional mean. And of course, just looking at it by the naked eye, you're already probably thinking, well, like f2 is much better than f1 and f3, because you're seeing something, you have some implicit notion of what it means for a function to fit the data. But here I'm just saying, forget about that for a second. Just say, like, let me throw random functions out there and say, it could be any of these. Like, I haven't even seen the data yet. These are all possibilities, right? So this is all I mean by a set of candidate functions. And you can have a finite set of candidate functions. So here I have three possibilities, and I want to say which one of these is it. But more generally, that's not the way to go, because you can't really ever enumerate a rich enough set of finite functions. And so more generally, the way that we actually think about these is an infinite set. So for example, here I have f, our script f, is our set of candidate functions, and I'm using it to represent the set of all lines. So here I've drawn three different lines, f1, f2, and f3, but we could imagine there's a lot of other lines that also we could consider as candidates. So for any slope at any intercept, we could draw a line. And so you could draw all the possible lines here, and it would totally fill the page, but that's what we're talking about when we say script f is the set of all lines, and we want to know which of these lines is the one that best fits the data. So this is our set of candidates. Okay, lines are nice, and this is a general property, not just lines, but many sets of functions can be parameterized. And what I mean by that is that you can describe each candidate with one or more numbers. So with lines, we can do that with a slope and an intercept. So if you remember from your basic algebra class, a line is represented by an equation: y is equal to slope times x plus the intercept, right? And this is the equation of the line, which means that this shape here, right? Basically, for each of these shapes, there's an associated slope and there's an associated intercept. And if I know the slope and the intercept, that tells me every single point along this line. So I don't really need to think about the set of lines. I can think about the set of slopes and intercepts. So here I'm showing, like, if I want to represent this function f1, I can draw f1 not as a line on a graph, but as a point on a plane, right? So I'm just saying, what is the slope of this line? What's the intercept of this line? Okay, and now this point represents this function. And similarly, if I had another function with a different slope and a different intercept, I could put it down here and another function down here. So, really these are all just different points. Like, for example, I don't know, if this is 5 and this is 3, this point here is, we would typically call it 5, 3. But all I'm saying here is like, okay, well, let this represent the function 5x plus 3, all right? So each point on this plane is representing a function over here. And that's what I mean when I say that they are parameterized. So these m and b I call the parameters of this function. And all I'm saying is that this function class, I can just summarized by just saying what are the values of the parameters of that function. That's the basic idea. We'll see why this is useful. Very useful. Okay. So, all right. So step one, I'm giving you an example of, let's just say our candidate functions are all lines. Step two, we need to pick a way to grade how well a candidate fits the data. So this is, now we can get back to our intuitive notion of fit. If we look at these three lines here, you may think, okay, well, F2, this is great, right? Big smiley face here. We're kind of fitting the data. F3, meh, kind of a meh fit. Like it is at least kind of going through the data, but it's sloping down, whereas the data kind of look like they slope up. F1, big frowny face. It's kind of way off the mark, right? That's all I mean by grading fit, is giving some kind of like A+, B- grade to each function in our set. All right. And however, we need to do that in a way that's not just happy face, frown face. We need to do that in a way that's quantitative. And the way that that's most often done is with prediction error. So you take a function and you can draw the line, and then you have your data points, and you can say how far off, right? So if I'm using this function, let's say for this value here, right? Let's say that's 5. So for a person who's 5 years old, what is this person's actual blood pressure was this, and if I were using this function to predict it, I would have predicted this. So that's a big difference, right, in what I'm predicting versus what I actually observed. And that is what we call the prediction error, or sometimes just error, or sometimes residual. These are all words that mean the same thing. It's just how far off is my prediction from the true outcome value that I observed. And the way that we use those residuals, in this case, we're going to use them to construct something that we call mean squared error. So this is how we're going to quantify whether we think this function is good or bad relative to the data. Does it fit? So we're just going to take those errors for each of the data points that we have. We're going to get the error, and we're going to square it. So the error is this difference, the actual observed outcome minus the predicted outcome, given this person's value of the predictor. I'm going to have that error. We're going to square it. The squaring, what that does is that it means that, so if the error is positive or negative, it contributes the same amount. And it also makes it so that big errors are more heavily penalized, because let's say that so this is error. So this is like error squared. It's going to look like this, because it's error squared. So if we have no error, great. That means we're not paying anything for it. But as the error gets bigger, going from here to here, we're paying a big increase. And if we go from here to here, we're paying an even bigger increase. So we're really penalizing these big errors, making these big errors. We want all the errors to be as small as possible. So what we're going to do with each of these errors, we're going to square them for this reason, and then we're going to average them. So we want the average error, averaged across all the data that we have, to be small. And that's our notion of how good a function is at predicting the data. And we call that mean squared error. So obviously lower values of mean squared error are better. It means that this function is better at predicting the data. And we can think of this as a function of a function. So here f is our candidate, our potential line that fits the data, and we want to know how well does it fit the data. That is what I call L of f. MSE is mean squared error. I use L here because this is one specific example of what is generally called a loss function, and a loss function is exactly what we're talking about. It's just some function that you give it your candidate function that says how good is it at predicting the data. So this is one way at quantifying how good f is at predicting the data. So here what's varying is f, right? Here I'm changing the different possible functions that I could use to predict the data. Y and x are constant. We have the data, that's fixed. We're just trying to mess around with f and see which one is good or bad. So this is exactly what we wanted. So now we can grade these. So if I have this potential, this candidate function f2, and I have these data, well, I can just compute the value of the mean squared error for this f, and look, it's pretty good. So I gave it a smiley face, and I can compute the error for f3, and it's kind of meh, and then I can compute this mean squared error for f1, and it's bad. So this is what we want. Now we've quantified what we mean when we say how good a function is at fitting the data. And in fact, why are we using this mean squared error? Besides just the fact that it kind of intuitively it makes sense that it's the prediction error, we square it to get them all to be positive, whether it's negative or positive, and blah, blah, blah. But actually, it's the case that the true conditional mean is the function. So I gave here the biggest possible smiley face, because this is the function that maximizes the expected mean squared error. And the proof of that requires a little bit of calculus. The idea was just to kind of justify why we use mean squared error a little bit. It's because what we're looking for is this conditional expectation, right? And so we would like a way of grading our set of candidate functions such that the thing that gets the best grade is indeed the thing that we're looking for, right? It's like we have like some pool of applicants to a job, and we know that we know who the star applicant should be. We need a way of coming up with a rubric. If our star applicant doesn't actually get the best score for our rubric, then it's not really a good rubric, right? So that's what we're showing here, is that this rubric that we have, mean squared error, actually indeed gives us this thing that we're looking for, this top applicant gets the best grade. That's what we're saying here. And we did a little proof for that. Okay, so now we have a way of grading these different candidates. We have a set of candidate functions, and we need to come up with an algorithm to search the candidates to find the best fit. So the easiest way to do that is to just guess and check. So start with a random slope and a random intercept. Evaluate the value of the loss function. Just compute it. How do we do that? We can just literally take all the predictions, subtract off the actual observed values, square those things, and then average them. We just do that for every candidate. And we see which one does the best. So this whole guess and check process does not give us actually the best fit line, because we're only considering 200 guesses, and we have no way of making sure that the actual best fit line is anywhere near any of our 200 guesses, right? So what are we going to do? All right, so here's an insight. Consider the loss, in this case mean squared error, as a function. And by the way, maybe we should explain a little bit more about this mean loss terminology. Why is it called that? Because the mean squared error and other such functions, so let's say, let's look at this. Graded guesses, okay? So this, you can think of this as MSE as like quantifying the fit, right? Where lower is better. So you can also think of this as like, how much are you losing? So if I use this function as my fit, how much do I have to pay? How much does it cost me if I'm believing that that's the truth, right? And here, this is what I'm paying. I'm paying this amount in error. This is my average squared error. And I'm just kind of thinking of that as like, that's a cost to me. That's how much I'm losing if I were to use this function. If I were to use this function, I'm losing even more, right? Here I'm losing like $167, where in this case I'm only losing $16. So generally, when people have a function that kind of grades these different candidate regression functions, they call that a loss function, because it quantifies how much you are losing in terms of error, or however you want to think of that. So there's just a little bit of terminology, loss function, or sometimes people also call it a cost function or an objective function. And all those terms are trying to get at the same thing, that lower is better. This indicates that you're paying a lot more spiritually to use a function that doesn't fit well. So the insight here in terms of why guess and check fails and what we can do about it is to consider the loss function as a function of the parameters. So instead of seeing it as, okay, you give me a function, I tell you the loss, a different function, I give you a loss. Well, let's use the fact that these functions are actually parameterized. Let me see if I have, no. All right, so let's go back all the way back here and remember that each of these lines, we can think of them not as like a line on a XY graph, but as a point in a space of slope and intercept. So I have my slope here and I have my intercept here, and this function is represented by this point, where this point is given by its slope and its intercept. So if I lay out all of our possible functions on such a little plane like this, and then I look at their I can imagine each of these has a value of a loss associated with it, and it's either high or low. So I can think about kind of plotting for each function the value of its loss, and think of it as like a heat map, where if it's like a really bright color, then that loss is very low, and if it's a darker color, that loss is higher. And that's what I've done here. So here I have slope and intercept. So for each function, I've imagined it as a point on this plane. And here what I've plotted is the log MSE, just to make the colors more distinct, but you can just in your head just imagine this is MSE, mean squared error, where lower is better and higher is worse. So we can see that actually the optimum is this thing where the slope is, and we saw this already, actually it's the point where the slope is 1 and the intercept is 0. That's the optimum. And that's where we're trying to go. So our guess and check strategy was bad because we were just kind of throwing darts at this, right? We were throwing 200 random darts at this plane, and wherever they landed, we were looking at the value of the loss, and we're saying which of them is the lowest, right? But there's no guarantee that we're throwing a dart right in the middle here, right? And it turned out that our closest dart was like slope equals -4, and intercept was -4, and the slope was like 1 or something like that. So our closest dart was like here, and the truth is here. So which in terms of the colors here looks pretty good, but there's actually still a big gap, and we saw that when we looked at the plot, right? Like that's pretty far from our data. So what we're going to do differently is, instead of throwing stuff randomly, we're going to iterate. So we're going to pick a first guess, and then we're going to try to go, if you think of this as a bowl, so like you're looking down into a bowl. So the contours represent like what in mathematics you would call a level set, where if you're looking down into a bowl, if you were to somehow slice that bowl kind of across your vision, you would kind of like chop off the top part of it. That's these kind of like contours. So it's kind of like a bowl that's coming up and out towards you. So what we want to do is get to the bottom. We're trying to get to the lowest loss in that bowl. And to do that, we're going to start with a guess, right? And we're just going to now, instead of picking our next guess randomly, we're going to go downhill. So we're going to follow the contour of the bowl towards the middle. So if we roll downhill a little bit, our next guess is going to be here, okay? And then if we iterate this procedure, again, we're going to get closer and closer to the minimum of the loss until we actually get down into the center of that bowl. And here the important question is, well, how do you know which way is downhill? Like if I make a guess, I figure out what the loss is there. Cool, I know this function is like good or bad or like medium or whatever, but how do I know which way to move the intercept and which way to change the slope to get it to be closer to the optimum? And it turns out that the derivative of the loss with respect to the parameters tells us how much to move our guesses. So because the derivative is kind of it's the slope of this bowl in each direction, and this is a little bit hand wavy. We can get into this. Anyone who's interested in this, feel free to follow up with me, and we can talk about it more. But the derivative, for free, if we know what this derivative function is, we can just evaluate it, and that'll tell us which way to go. And so as a concrete example here, so let's say that we're using mean squared error. So here we want the derivative of the mean squared error with respect to the slope. And this is going to tell us how much we should change the slope. Should we increase the slope? Should we decrease the slope? From our current guess. This is how we're going to do it. So we need to take this derivative with respect to the slope. The slope is actually some parameter of this function. So we can actually replace here where it says f of x, we can put in this is equal to m times x plus b, right? So we can just plug that in, and now this whole thing up here is just some function of m. and we can, if we want, we can put that into Wolfram alpha and take the derivative with respect to m, and what comes out of that, if you do that, is this. This is the derivative of that thing with respect to m. So it depends on the current value of m, right? This is our current guess here. And so we just have to plug our data into this. So for R, for example, this would be like mean of like x times y minus m times x plus b, right? So you could have this all coming like from data. And then this would give you my next guess for m. So whatever this slope is here, that'll give you the next guess. So it would be going for example, if this were the current value of the slope here, it would say, oh, the next value should be here. So it tells you how to change that. You would do the same process for the intercept. You would have to take the derivative of the, not with respect to the slope, but with respect to the intercept. So you have to change that. You would get a different thing here. So if you did that, that would tell you how much you needed to change your intercept to go from here to here. But you're guaranteed to be decreasing the loss if you follow this kind of recipe. If you're always going in the direction of the derivatives, you're always going downhill. And so this algorithm is called gradient descent. Gradient refers to the derivative. Gradient is just a word that means derivative in multiple directions. So you have the derivative in terms of the slope and the derivative in terms of the intercept. It's just telling you how is this function changing if I decrease or increase the slope or intercept. And so if that function is going down, then you have a negative derivative. Derivative gradient is just when you have multiple derivatives stacked together. We call it a gradient, or you could think of it as a direction, which is like the relative magnitude of how much the slope is changing versus or how much the function is changing if we change the slope and the intercept a little bit. And so if we're following the gradient downwards, we're descending the loss according to the value of the gradient. That's why this thing is called gradient descent. And so this is an iterative algorithm where instead of just guessing and checking, we're throwing a whole bunch of points at here and seeing which one is good and bad, which is very inefficient. It's not good. We're iteratively first making an initial guess and then updating it and then updating that and then updating that at each point following the gradient downhill. And this is how we get the solution. In other words, the final intercept and slope that are the optimal values. Now, some of you who have looked at gradient descent before, maybe in 142, or you may have seen that actually there's this analytic solution. So I don't need to do this at all. I can just kind of plug in stuff into this formula, and that gives me the optimal slope. But I think this is kind of obscures the point of regression, which is that the intuition is that we're just going downhill. We have a space of functions, of possible functions. We want to assign some kind of grade to them that says what's good and what's bad in terms of how well they fit the data. And then we just want to go downhill, all right? We want to go and we want to find the function that best fits the data. In other words, the function that has the lowest loss. And so I think understanding gradient descent is really nice because it's actually a much better intuition than just looking at some formula and saying, well, magically you multiply and add these numbers together and that gives me the slope that best fits the data. Like, I don't know, I just think that's kind of meaningless. And also to get to this formula, you have to kind of understand, if you want to derive it, you need a bit of calculus and stuff like that, which is okay, it's not that bad. I mean, ideally you kind of understand both in the context of each other, but by itself, understanding this like just more general idea of regression is better, I think. Also because gradient descent can be used for any parametric model. So what I explained to you, you actually just learned how to fit everything, not just linear regression, but you've just learned how to fit logistic regression. You've just learned how to fit a Cox survival model. You've just learned how to fit a neural network. So this is a very simple case where there's two variables, right? Just the slope and the intercept. But you can actually apply this algorithm even if you have 1,000 variables. So if you have 10 slopes and an intercept, or if you have, for logistic regression, the only difference between logistic regression and linear regression, and we'll get to that, is that you have a different set of candidate functions and they're parameterized differently. So you don't have, there's still like a slope and intercept, but then you've wrapped that into some other thing. And same with Cox models. It's just a different set of candidate functions. Neural networks, it's just a really big set of candidate functions. Neural networks is like, you take a logistic regression, you glue it onto another logistic regression, you glue it onto another logistic regression. But at the end, you just have a large set of parameters, and you want to find, you can think of these as like little knobs, right? So here you have an intercept knob and a slope knob, and you're kind of trying to tune these things to get the setting that gives you the lowest loss, the best prediction error. So in a neural network, you can think of like a soundboard, right? Or like if you're in the recording studio and you have all these different little knobs that are changing all these different like parameters of the sound, and you're trying to produce a record, right? And you're trying to tweak all these to be just right. That's the neural network, right? You basically just have way more parameters than this very simple case where you just have two. But you can play the same game. You define your loss function, and then you say what's the derivative of the loss function with respect to each of these parameters, and you actually don't even need to derive that. It can be done automatically because the rules of taking derivatives are like simple enough that it's pre-programmed into these packages that you can use to make neural networks. It'll automatically find all those derivatives for you, and then that tells you, if you just have an initial guess, like you set these knobs to something, take your hands off, say, okay, this is my initial guess. You press play, it'll say, here's the next guess that you should guess, right? So it'll tweak all those knobs in such a way that the loss function goes down a little bit. You're like, okay, cool, let's go again, and it'll just keep tweaking all these little knobs until you get a function that fits better and better and better, and then finally you have something that is like the optimum. And that's how linear regression is fit. Even though there's this formula, actually a lot of the algorithms that actually do this do linear regression because it's faster than evaluating this, or do gradient descent. It's actually faster than evaluating this formula sometimes. That's how logistic regression is fit. And there are little bells and whistles that I haven't told you about, but this is the basic idea. It's how Cox models are fit. It's how ChatGPT is fit. ChatGPT, okay? Huge, billions of parameters is just gradient descent. So understanding this, I think, is really, really helpful and much more general than looking at some formula. So that is all regression methods. And what we talked about with linear regression is just this particular choice of these methods, right? So for candidate functions, we just picked linear functions. For a way to grade them, we said we're going to use mean squared error as the grading tool, or our rubric. And then to search among these candidates, we're going to use gradient descent, as opposed to like guess and check. And there are other algorithms that you could consider that we haven't talked about, and there's bells and whistles on gradient descent. But this is like by far the most kind of like generic way to do this. This is like the canonical example for regression. And now you know, that's linear regression.